Okay, 2.3b, investigation. So we're going to investigate vertical and horizontal translations of functions. Number 1a, complete the following table of values for the function f at x equals x squared. Okay, so that's our normal parabola. G at x equals x squared plus 1. Okay, so what we're going to find out here is that these are going to go up 1, essentially. And h at x equals x squared minus 4. So this is our parabola going down 4. Okay, so if we were to fill in the coordinates for the base function x squared, we would get 4, 1, 0, 1, 4. Okay, so those ones we basically have memorized from grade 10. Now what we're going to do is we're going to do x squared plus 1. So if you want to take your calculator and do negative 2 squared plus 1, and then negative 1 squared plus 1, and then 0 squared plus 1, and so on to all of these points, what we're going to get is 52125. Oh, I'm going to color coordinate this. This is now going to be green. That looks better. Okay, and this one's going to be red. H at x is going to be x squared minus 4. So again, if you want to take your x values and plug them in, negative 2 squared minus 4. Negative 1 squared minus 4. 0 squared minus 4. What we're going to come up with are the points 0, negative 3, negative 4, negative 3, 0. So graphing these, I'm going to graph the first one here in blue. That's going to be our original parabola that we're all familiar with. Okay, so this is just x squared. You put f at x. I didn't use function notation here, and that's okay. Okay, if we were to graph these, we would see that this graph is going to lie here. And this is going to be x squared plus 1. Let's g at x. That's fine. We'll call this f at x. Okay, and then if we take our h at x, we're going to notice that this is going to graph here. So this is going to be x squared minus 4, and this is our h at x. Okay, so we have these three graphs now. Okay, so the question is, are these congruent? Okay, so all three of these graphs are congruent. If you took the blue one and you shifted it up, you're going to get the green one. And if you shifted it down, you're going to get the red one. So yes, they are the same shape and the same size. Okay, now we're going to state domain and range for each of these. Okay, so let's set up domain and range. For the domain, we can tell that every single parabola goes to the left and the right infinitely. So we're going to simply do XER for all of them. Now the ranges is what's going to differ. So we'll open up the ranges with y is an element of the real number system. But there's going to be a restriction on the ranges, okay? So we want to take a look at the vertex. Okay, so on the vertex of the original one, we're at y equals 0, and then our parabola opens up. So y is greater than or equal to 0. Okay, remember this is our k value of the vertex. This is our optimal value. Okay, so like the y of the vertex. Now, if we take a look at the second one, that one, the vertex is at a y value of 1. So y is going to be greater than or equal to 1. And if we look at the red one, our y value is at negative 4. So y is greater than or equal to negative 4. So now describe how you would obtain g at x and h at x from the original graph. Well, This simply went up 1 unit. This one went down 4 units. So when we continue to graph, what we're going to do is we're going to look at this value here that's trailing behind the function, and that's going to indicate up or down. Okay, 2a, complete the following table of values for our original function, f at x equals root x, g at x equals root x plus 3, and h at x equals root x minus 2. So this is going to be our original here, root x. When we root all of these x values, we're going to get 0, 1, 2, 3. Okay, when we root x and then add 3, right, g at x equals root x plus 3, we're going to get 3, 4, 5, 6. And for h at x, we're going to do root x minus 2. And I mean, if you guys need to sub these x's in, you can go ahead and sub in root 0 minus 2, root 1 minus 2, root 4 minus 2, and so on. Okay, so we're going to get negative 2, negative 1, 0, 1. If we were to come down here and plot these on our graph, this is our f at x. Oh, this one goes a little bit off the graph. That's okay. This one's going to be our g at x. And then this one's going to be our h at x. Okay? So the question is, are these graphs congruent? Yes. They haven't gotten skinnier or bigger or shorter or fatter. Okay, so they're congruent. They're just shifting up and down here. Okay? Now, domain and range, I'm going to set this up. Okay, so what's going to happen with our domain and range is we're going to look at where, I don't want to call it the start, but basically the start, or I also call it the vertex on its side. So if you're thinking of this as a parabola on its side, we're going to take a look at like what would be considered the vertex, right? So for the blue one, the vertex would be considered basically 0, 0. So x is going to be greater than or equal to 0, and y is going to be greater than or equal to 0. Okay, all three of these graphs are still going to the right forever and up forever. So we use the greater than or equal to sign. Okay, for the green graph, we're looking at the point 0, 3. So for the x, we're going to use 0. X is greater than or equal to 0. For the y is greater than or equal to 3, right? We use these 2 points coming straight from the vertex. Okay, and for the last one, we have 0, negative 2. Remember, this is the x and y. Okay, so x is going to be greater than or equal to 0. Y is going to be greater than or equal to negative 2. So taking a look at these graphs, we know that like the blue one is the base function, the green one is moving up, and the red one's moving down. So when we look at these graphs, and we want to describe what's going on with these graphs, this graph here moves our root x function up 3. This graph here moves our root x function down 2, and we'll put units. We don't know what the units are, so it's the general form. Okay, number 3, complete the following table for the base function f at x equals 1 over x. Okay, so this is our rational function. And then g at x equals 1 over x plus 4, h at x 1 over x minus 2. Okay, so from our original graph, 1 over x, we know that we plot the points -1, -1, 1, 1. We have a horizontal asymptote of y equals 0 and a vertical asymptote x equals 0. Okay. Now for the second one, 1 over x plus 4, if we were to substitute 1 over -1 plus 4, we would get 3. Okay, and 1 over 1 plus 4, we'd get 5. Okay, so here's the thing. This here affects, this is going up 4. That's going to affect our horizontal asymptote. So our horizontal asymptote is graphed, and it's going to move up 4. Okay, so our new horizontal asymptote is y equals 4. Our vertical asymptote stays the same. Okay, and for the last one, 1 over x minus 2. So I get -1 minus 2, I get -3. 1 minus 2, -1. Our horizontal asymptote is now -2. Whatever this number is, that's our horizontal asymptote. Our vertical asymptote doesn't change. So I'm going to go ahead and graph these. So this is going to be f at x in blue. And we have y equals 0 and x equals 0 as our horizontal and vertical asymptotes. And we have our curves in these corners. Okay, you see how these curves are opposite from one another, to one another? They're always going to be like that. Okay, now if we were to move this up 4, we get the same vertical asymptote. Okay, so I'm going to leave that there, but this time we get the horizontal asymptote y equals 4. Okay, and this is going to be our g at x here in green. So if I were to plot this, -1, 3, and then 1, 5. What I know about this is that we have vertical and horizontal asymptotes splitting this graph, and wherever there's one point, we only need to know one of them, because then that's where our curve's going to lie. Okay, and for the last one, same vertical asymptote, now horizontal asymptote at y equals -2. And this is going to be our h at x. Okay, again, if we plot -1, -3, and 1, -1, these two, I almost want to call them quadrants, okay, because with the vertical and horizontal asymptotes, we're cutting our graph into 4. And wherever these 2 points lie, that's where we're going to plot our curves. Okay, now, are these graphs the same size and shape? Yes, they're just moved around. Okay, and state the domain and range of each of these functions. So the domain and range of the 1 over x function, we can always set it up like this. X is an element of the real number system such that x does not equal. Okay, and we can set each and every one of these up. X is an element of the real number system such that x does not equal. And for the range, y is an element of the real number system such that y does not equal. Now, what we're going to fill in here are in the numerator, or sorry, not in the numerator, in the x does not equal, we're going to fill in the vertical asymptote. And in the y does not equal, this is going to be the value of the horizontal asymptote. So for the original, it's 0, 0. In this question, we've only shifted up and down, which doesn't affect the vertical asymptote since it just shifts up onto itself. So all of the vertical asymptotes are a 0 here. And if we take a look at this value right here and this value right here, these are going to be our new horizontal asymptotes. So y is not going to equal 4 and y is not going to equal -2. Okay. And how we would describe these graphs is up 4 units from the original and down 2 units, again, from the original base function. Okay, number 4, complete the following table of values for the base function x squared. And then we have g at x equals x minus 2 squared. And then h at x, which is x plus 3 squared. Okay, so we know our base function is 41014. Now, if we put these, and just pay attention to the x values, I made sure that the x values worked out very well. Okay, so negative 2 squared, we would get 4. Negative 1 squared, we get 1. Okay, so if we filled this out, we would get these points again. And now the same thing here, negative 5 plus 3 squared, which is just negative 2 squared. So we would get 4, and again, 0, 1, 0, 1, 4. Okay, so I did this so that the vertices would be in the middle here. So let's go ahead and graph these. So we all know what the base function looks like. That's easy. Okay, and this is our f at x. Now, f at x minus 2. Remember, this is in vertex form, if you think about it. And we know that this vertex would be, well, 2, 0. Okay, so this is going to be our g at x. And h at x. A red one. Okay, we would know that our vertex is negative 3. Oh, I did this backwards. 2, 0. I was reading this as negative 2. This is 2. That's better. Okay, so this is g at x. And then h at x. This is negative 3, 0. So that's our vertex. And this is going to be h at x. Okay, and if you guys notice, the vertex actually runs in the middle all along here. So when we're applying transformations, the vertex is going to map onto like the next vertex or the transform vertex. Okay, so yes, all of these graphs are congruent. They're all the same size and shape. They just move over to the right or the left. Okay, so I'm going to set up my domain and range by starting with XER, YER. Okay, I would get into that habit. X is an element of the real number system, and Y is an element of the real number system. Okay, and now we can talk about our domains and ranges. So the domain of any parabola that we know is XER because it extends to the right all the way and to the left all the way. Okay, and that's unless there's a restriction on it due to like if you put in a word problem, if there's like time or height or something like that. Okay, now what we do is we look at the vertex, and whatever the vertex is, we look at that y coordinate, and then if it opens up or down. So for all of these, the y coordinate of the vertex, and we can see this even in our charts, is 0. And all of these open up, right? So in all of these, y is going to be greater than or equal to 0. So what we can actually say about these graphs are like, the blue one is the original. The green one shifted to the right 2 units. The red one shifted to the left 3 units. So down here, how would we describe what happened? This one shifted right 2 units. This one shifted left 3 units from the original function or from the base or the parent function. Okay, complete the following table of values for our base function, root x, and then we're going to graph x minus, or root x minus 3, then we're going to graph root x plus 5. Okay, so for the original, root x, we know our base points, 0, 0, 1, 1, 4, 2, 9, 3. Now, just pay attention to the x's because, again, I made these super pretty for this example. So what is root of 3 minus 3? What is the root of 4 minus 3? What is the root of 7 minus 3? Right? We're substituting all of these x's into this value here. Oops, I should do this in green. Okay, so I get 0, 1, 2, 3 as well. And if you do the same thing for h and x, we're going to get, again, 0, 1, 2, 3. Okay, so for the first one, the original function, this one, just like the root function, this one's going to be memorized in no time. Okay, now we're going to go 3, 0, 4, 1, 7, 2, 12, 3. And this is going to be g at x. Now we're going to go negative 5, 0, negative 4, 1, negative 1, 2, and then 4, 3. And this is going to be our h at x. So if we're taking a look at these functions, we can say yes, they are identical. They're just shifted left and right, if you think about it. Okay, they haven't been stretched or compressed. Now, I'm going to set up all three of these domain and ranges, and we set them up all the same. Okay, so formally, our domain is x is an element of the real number system, such that, and the y as well. For these ones, we're going to have a restriction on both the domain and the range. Okay, so for these ones, what we want to do is we want to go to where, if you think about it, like the vertex, the fake vertex on the side would be. Okay, so for the first one, the vertex is at 0, 0. Okay, and we know that all three of these open to the right and go up forever. So simply, x is going to be greater than or equal to 0. Y is going to be greater than or equal to 0 as well. For the second one, our fake vertex is at 3, 0. So just remember, this is the x and this is the y. So x is going to be greater than or equal to 3. Y is going to be greater than or equal to 0. Again, we go to the right forever and we go up forever. Okay, nothing's been reflected. There's only one arrow on each of these graphs, and it's going to the right and up in those directions. Okay, the last one, we have our fake vertex at negative 5 and 0. So x is going to be greater than or equal to negative 5. Y is going to be greater than or equal to 0. So if we look at this graph, we can see that the green one moves to the right 3 units. The red one moves to the left 5 units. So when we take a look at this transformation here, I'm going to say right 3 units. This one is going to be left 5 units. Okay, when comparing these to our base function. Number 6, complete the table of values for our base function 1 over x, and then g at x 1 over x minus 4, and then 1 over x plus 3. Okay, so we know that the original graph has the points negative 1, change this to blue. Okay, negative 1, 1, 1, horizontal asymptote of y equals 0, vertical asymptote of x equals 0. Okay, if we were to plug these points into here, and remember 3 and 5, I made these really nice for us. Okay, I made these so that it recenters our graph. So I get negative 1, 1. Now our horizontal asymptote, moving left and right, doesn't change. But this is going to change our vertical asymptote, right? Because this essentially is telling us that we're going to move to the right 4. right? It's going to be opposite of that sign. So it's not left 4, it's right 4. So we're going to have a vertical asymptote of x equals 4. Okay, and now again, I recentered this graph for us, so it's easier to read. Y equals 0 because it doesn't move up or down. And the vertical asymptote is going to be x equals -3, since this moves our graph to the left 3. Okay, our original is here and here. We have to mark our vertical and horizontal asymptotes. Okay, our new one. First you want to draw, so that one I just sketched, but if you noticed, I drew the vertical and horizontal asymptotes first. Okay, horizontal asymptote y equals 0, so that stays. Vertical asymptote x equals 4. Now when we plot these points here, we're going to plot it in, like, considering if these are quadrants, this quadrant and this quadrant. So again, it's going to approach the horizontal asymptote forever, both ways, and the vertical asymptote up and down forever. Oh, and I have to label x equals 4. Okay, now the last one, y equals 0. Okay, I'm not going to label that again, I already have it here. And x equals -3. X equals -3. So if we plot our 2 points, our graph's going to look like this. Okay, this is h at x. The green one is g at x. And our blue one is f at x. All color coordinated. Okay, so all this is, if we started at blue, we would go to the right to get green and to the left to get red. Nothing flipped, nothing changed. It just simply moved. So yes, these are congruent. And now I'm going to show you how to set up the domain and range. Okay, we're going to start by saying x is an element of the real number system such that x does not equal. Okay, so every single one is going to be set up like this, and the range is going to be set up as y is an element of the real number system such that y does not equal. Okay, and what we put for the x is the vertical asymptote, and what we put for y is the horizontal asymptote. So we can either look at the graph or we can look at these. Okay, so the first one, 0, 0. Okay, x does not equal 0, y does not equal 0. Now the second one, 0 and 4. If there's a vertical asymptote at x equals 4, that means x will not equal 4. If there's a horizontal asymptote at y equals 0, that means y does not equal 0. Okay, and the last one. If there's a vertical asymptote at x equals -3, that means that's a restriction. X does not equal -3. And then the y does not equal 0. Okay, so how would we describe these graphs? This graph moves right 4 units, and this graph is left 3 units. So conclusion. In regards to vertical and horizontal translations, vertical translations are in this form here. So whatever function it is, and we talked about base functions, x, x squared, root x, or 1 over x, whatever function it is, if it's a vertical translation, it's going to be whatever number is here tacked onto it, okay? Like on the end, so plus c. So if c is greater than 0, in other words, if it's positive, then we just move that base graph up. And if it's negative, we move that base graph down. Okay, now if the number is inside of the bracket with the x, then what happens is this is when, so this is like minus h, and it's minus h in this bracket here, minus h all under the root, or minus h in that denominator. What happens is if h is positive, we move h units right, and if h is negative, we move to the left. Okay, just remember that built-in negative sign. Okay, so whatever sign it is, it looks the opposite.